Thank you for joining the April 2025 VMware TAM customer webinar. This webinar is organised by the VMware TAM organisation to provide our customers the opportunity to interact with great speakers about content that will help them get the full benefit from their VMware software. Before we get into today's session, there are just a couple of basic announcements. Our next TAM customer webinar will be on May 15th, where we will cover part 2 of the key features of ARIA operations for networks with Matt Just, this time with a focus on troubleshooting. If you missed part 1, please ask your TAM for access to the recording. Your interaction during this webinar is important, so please make use of the Q&A feature of Zoom to ask any questions. If we're unable to answer your question during the webinar, please reach out to your TAM and ask them to follow up. At the end of today's session, you will be prompted to fill out a simple 2-question survey related to the value you received from this session and any topic suggestions for future sessions. Your completion of this survey is a very valuable gift back to us, and we'd greatly appreciate if you could take the time to complete that. And lastly, this webinar is being recorded and your TAM can make the recording link available to you. After a few months, the recording will be publicly available on the VMware TAM Services YouTube channel. And so that brings us to today's speaker and topic. It's my pleasure to introduce Justin Murray, Product Marketing Engineer within the VCF division. And Justin's going to provide us with a technical overview of Private AI Foundation. So over to you, Justin.
Thank you very much, Ami, and welcome everybody. Thank you for joining us for this webinar. I'm Justin Murray. As Ami mentioned, I'm a Product Marketing Engineer in VMware Cloud Foundation in Palo Alto in California. So I'm going to give you a technical overview of VMware Private AI Foundation with NVIDIA in the next 80 minutes or so. I want you to leave this event with a lot more comfort on what the terminology we use is around Private AI Foundation and a good feeling of how it really works. So that's my objective here. I have a lot of agenda items here. I'm not going to cover all of these in great depth. I'm going to leave the NVIDIA licensing to another day, but this is a general purpose talk that I give to our customers who are adopting VMware Private AI Foundation with NVIDIA. And I'm going to start off with some really high level and fairly simple terminology, just so as we're all speaking with the same meanings and words to begin with. And then we'll get into the deployment options and GPU monitoring and model store. And I'll sprinkle a few demos into this as well. So this is the big picture of VMware Private AI Foundation with NVIDIA. It's really the blue layer in the middle of this diagram, which is, as you can see, heavily focused on VMware Cloud Foundation. VMware Cloud Foundation is a prerequisite for using Private AI Foundation with NVIDIA. And the VMware Private AI Foundation with NVIDIA is actually an advanced set of services that you provision into a VMware Cloud Foundation deployment. So if you've already got VCF, you can get VMware Private AI Foundation and install it there. And it has several parts to it: model governance, vector database, self-service automation, and GPU management and optimization. I'll get into those in more detail. What all of those, if you like, infrastructure pieces enable is the data science things at the top. These are NVIDIA components. So the assumption we make when we deploy VMware Private AI Foundation with NVIDIA is that you're also interested in using NVIDIA AI Enterprise, a suite of software from NVIDIA that's composed of various tools for the data scientists, like a runtime for their models, for example, a runtime for the large language models, which are going to be running on premises in this case. And that's the NIM microservices in the top left-hand side, or a retriever for fetching data from vector databases. And I'll explain why that's important as we go along, or some blueprints or application designs that you can get started with. And we'll talk about a particular one called Retrieval Augmented Generation, or RAG. I'm going to talk a lot more about that. And finally, there are various operators, which are Kubernetes functions for deploying all of the 3 things on the left-hand side into Kubernetes. So think of those things in the green layer as containers that you fetch down, or we fetch down for you using the self-service automation from NVIDIA's GPU cloud, actually, NGC. And we deploy all of those things for you so that you don't have to worry about getting them started. So a data scientist walks into Private AI ready to go. They're in a Jupyter notebook. They're using a Jupyter notebook with Python and PyTorch, which are the tools of choice nowadays. And all of that's running on VMware Cloud Foundation, and all of it is already certified by the OEM vendors that you see at the bottom: Dell, HP, Lenovo, Supermicro. At the very end of my talk, you will see some real models from those vendors, and Hitachi and Fujitsu as well. Some real models on our website that describe models that have been tested with all of this so far. This is a shipping product. It's been generally available since May 2024. We have multiple customers using it at the moment, and multiple other customers doing a proof of concept with it. So now, what's the terminology that you need to understand this? I'm going to go through 5 or 6 or 7 things here in short order, less than 10 minutes. I'm sure you're familiar with what a large language model already is. You've used ChatGPT, or you've used Google Cloud, or you've used Perplexity AI, or one of these fancy chatbots already. And this whole talk is really about building your first chatbot that's running on premises, as opposed to running against one of those public clouds. And the reason we want you to do it on premises is because you have sensitive company data on premises. So these large language models are trained by companies like Meta or Facebook, by Google, by Microsoft, OpenAI, by smaller companies out of France called Mistral, for example. These companies spend a lot of time and effort training them. And many of these companies now, Facebook started this about 2 years ago, have delivered those large language models into the public domain for use by you as an enterprise. So essentially, a large language model is a set of AI algorithms that uses deep learning techniques. Those techniques are called neural networks on large pools of data, so that having been trained on that large pool of data, perhaps it's everything on the internet even, having been trained on those large pools of data, the large language model can now stand alone and generate new language, as you've seen with ChatGPT, new terminology provided with a question. And we're going to see that in action. Now, so Llama 3 or Llama 4 now from Meta, Llama 4 came out this very week, in fact, the middle of April. These are examples of models that come from these large, tried and trusted companies, and are actually very good at processing your own private data if they're given some help with that private data. And the way in which we help a model talk about your private data is we build something called retrieval augmented generation, which is really fancy terminology for helping the model by means of data in a database. In other words, augmenting the model with data that came from a database, Retrieval being the database. So this is a design for applications that we're pushing at our customers. In fact, every company in AI is talking about this. If you go to a conference, there are tons of talks about retrieval augmented generation, because it solves a fundamental problem with these models, which is they can make something up. You don't want them to make something up in a business context. You want them to use the actual data in your company, like all the web pages that are private inside VMware on the next release of our GPU technology, for example. If I had to answer that question today, I would use a chatbot to find all those documents, summarize them for me, and present them. And those documents are held in a private database inside the company here. So retrieval augmented generation means adding to a model a database that contains private data to your company, data that you would not supply to a public cloud. So this is often used with chatbots and digital assistants. And the key component of this design is a vector database. Now, a vector database is a relational database under the covers, like Postgres or other databases. And so there's nothing mysterious about a vector database. It's just a relational database with a new data type called vector in it. And I'll explain the reasons for these vectors in a minute. But what's going on in a retrieval augmented generation is we're using one of these large language models running on premises, let's say Llama 4 from Meta, and we're complementing it with a Postgres database that we've supplied to you, and we've layered in the vector layer into it. That's called PG Vector. Postgres vector, into which you've stored some of your private documentation, which now can supplement or augment the model and force it to give the correct answer to a question. So that's the combination that we think is the on-ramp application, the first application that many of our customers want to do with AI in general and large language models in particular. And so the vector database is a private database used to store and index private company data. This is the private AI part. And it's used to power high-speed search based on a query. As you know, databases take queries in SQL. Well, this query is coming in natural language. And the query results that come out of the database are really sections of your private documents, chunks of your private documents that are pertinent to the user's question. The user has asked a question in a user interface called a chatbot. And so those results, maybe they're everything to do with GPUs on VMware that I've asked a question about. Those results are passed to the large language model, and the large language model summarizes them, massages them into a nice answer. The large language model completes the answer. It's called a completion model. So that's how vector databases help or augment a large language model. And we have tooling for this that comes with Private AI Foundation, VMware Data Services Manager, that can deploy all of this, including the vector part, in a friendly way for you. So pgvector is an open source extension to PostgreSQL. As you know, VMware has a lot of authorship on PostgreSQL. We had some of the designers of that working for us here. And we provision that into a VM or set of VMs for you using our Data Services Manager tooling, which is a general purpose tool for provisioning any kind of database. And entries in this vector database capture the relationships and similarities between the data that it knows about and the question being asked by the user in the front end. So this is used for storing data in a form that we call embeddings or vectors. The word embeddings is bandied about a lot by data scientists. Embeddings simply means a numerical representation of the words in the document. The numerical representation allows us to find similarities, allows us to find meanings between the different words. And these large language models are manipulating words. In fact, their prime function is generating a new word based on all the previous words in the sentence. So that's what's going on in pgvector. It's providing the vectorization or the embeddings technology to allow you to store your documents in a relational database in this numeric or embeddings form. So now you've got quite a lot of data science under your belt already. And don't worry too much about these terms. They'll come natural to you after a while. Now we move into the VMware side of it. So we have technology that allows you to provision special kinds of virtual machines called deep learning virtual machines that contain tooling that we've placed in there already. We ship you a virtual machine image with private AI containing Python, the language really that all data scientists are using, and Conda to manage that, and various other things as well, already in the VM. And that VM has been prepared to accept a GPU, provided you've got the GPU hardware. This VM can be allocated that GPU. That allocation is called a virtual GPU profile. But VMs need to be set up with various parameters to do that properly. We do all that preparation for you. So these deep learning VM images are used by our automation technology, previously called ARIA automation, now called VCF automation. VCF automation, you'll be interacting with me here in the demo, provisions these these deep learning VMs images, and we call them an AI workstation. It's a testing place for the models that we've just described. Okay, that's the first part. Very familiar. It's a VM. It's running various data science things inside it. And then we configure it with all of the NVIDIA tooling that I mentioned in the green layer at the top, the containers that NVIDIA supplies for real data scientists to do real work, like running a model, for example, and seeing if it works. Training and inference are very general terms. We'll come to those in a second. Here's what a deep learning VM looks like in a very familiar vSphere client. The unique thing about this deep learning VM called DLVM here is it's got two PCIe devices in the tile in the middle there at the bottom called Grid A140C. That's a virtual GPU profile. That's actually a virtualized GPU, and it's virtualized in the sense that we can vMotion this VM around in the data center. Even though that GPU has 40 gigabytes of memory on it, that's what the 40C means there at the end. And this VM actually has two of those. It has two A100 GPUs to itself here. It could be sharing those GPUs, and that's very common in inference mode in particular. So this allows me to treat the AI workload in a virtual machine just like every other workload that I've been managing for many years. It's just virtual machines under the covers, even when it's Kubernetes. And the GPUs are added to the VM in an automated way, and they're represented as virtual GPUs. This is a technology that comes from NVIDIA, but VMware works with them closely on the engineering of it, the virtual GPUs. We'll say more about that later on. But you can assign one GPU, two GPUs, four, eight GPUs to one VM, or you can assign a small portion of a GPU, like 1/7 of a GPU to a VM. It's very, very flexible. Okay, and that's how the image of the deep learning VM comes to you. It comes to you to be placed into a content library, and it's cloned from there. Now, I went through the process of cloning this VM by hand. That's the last time I'll do it. I'll use automation from now on because it makes the job much easier, much faster, and just more user-friendly by far to use our automation to clone this and set this up properly. Two kind of general terms that I need you to have at the back in your back pocket are the training of a model. There is this term called foundation model training, which is training a model from scratch. And we're not actually advocating that you do this. And I'll give you the reasons why. But this is the process of taking everything that's on Wikipedia, everything that's in every library in the world that's been digitized, and feeding it to a model over a period of weeks or months to bring the model up to speed on language in general, about every subject that you can get your hands on. And large companies, 4 or 5 large companies, Microsoft, Google, Meta/Facebook, and others, do this and produce models on a regular basis. This is called foundation model training. It's a tough one. It requires a lot of GPUs and a lot of data scientists and a lot of guidance to get it right. But this is training a model. Effectively, it has some parallels to the software development phase of software, but not quite the same. It's feeding very large quantities of data to the model and having the model recognize the patterns that are in that data so that it can reproduce those patterns later on. That's training. That's kind of the development side of large language models. We're not going to focus too much on that, apart from a very small subset of it today. We're going to focus more on inference, which is the production side of large language models. Training has been done. It took a couple of months or 6 months to do the training. That's how long you need to use many, many GPUs to do training. Now the model has been fully trained and it answers questions in an accurate and highly performing way. The model does. So we're going to put that model into inference, into production. This is really the payoff in AI. The training is the expensive investment of money by these larger companies, but inference is the payoff. It's the use of a model in an application after it has been trained on that huge quantity of base data. So the model now works on the new data. It can do many things. It can predict words in a sentence. Therefore, it can construct whole new paragraphs. It's doing that based on patterns it learned at the training phase, but the training phase and all of that data has been left behind. The model is now standalone and working on its own without referring back to its training data. It understands patterns now because it was trained. And inference is really the focus for us in VMware Private AI Foundation with NVIDIA, because this is what many of our customers will do. They'll take a model that has been trained by somebody else. They'll test the model in a deep learning VM to make sure it's accurate and it's not unsafe. It's not biased. It's not hallucinating, which is making stuff up. It's a safe model, and we can recommend some of those models to you. And they'll put it into inference alongside the database. That's the key message here. Okay, so the reason why we're not advocating training the model at a foundation level from scratch is because it takes thousands of GPUs, months of time, a large team of data scientists. You can read about this on the white papers that these folks have written. Microsoft and Meta have written white papers about their work here. And actually, you can come up with a model at the end of all this that isn't very good if you're not very careful and skillful. So high cost consumes a lot of energy, and there's a high risk here. Not something for the faint of heart. We have one or two very, very large global customers that are interested in doing this, but really the retrieval augmented generation plus inference is the way we think you should go in your first experiments here. So the problem that retrieval augmented generation solves is this set of problems here. A large language model on its own, without any augmentation, without a database backing it up, can get the answers wrong. We've all probably experienced this. It's not up to date with your current data. Its knowledge is only of data that was used to train it. That might be a few months ago. And the model doesn't tell you where it got the answer for any question that you supplied to it. It doesn't give its references. So the techniques being deployed right now to solve that problem are prompt engineering, fine-tuning, and retrieval augmented generation. And we have a strong recommendation of retrieval augmented generation as the place to start. Prompt engineering and fine-tuning are very respected techniques, and you can apply those alongside retrieval augmented generation, but we suggest to our customers that they start with RAG, or retrieval augmented generation, on a model that's been pre-trained by somebody else. That's Llama 4 from Meta, or Mixtral, a mixture of experts model from Mistral, or Falcon from the Research Institute in Dubai, or many others that are now what I would call open weights models. That is, those companies have supplied those models into a repository. That repository is called Hugging Face. NVIDIA has models of this kind also in their NGC, NVIDIA GPU Cloud. And those models have been tested by those companies, and those models are suitably licensed. They're licensed in such a way that you can use them for commercial purposes. That's the prerequisite that you apply to any model that you choose here. And we have a team of people who test these models for our own reasons. But the idea is that you're leveraging all of the training that Meta or other companies have done, and you're using the model with a specific smaller set of data that belongs to your company. You're supplying that through a vector database. So the vector database is augmenting the model, and we cure the problems of updates because we update the database with our new data every week or every night or every month. Updating a database is a very familiar thing. We do a mass load of data to begin with, and then we update on a nightly basis. This does not change the model in the slightest bit. The model is not aware of the vector database being updated. We are sure that the data that we put into the vector database, because it's private, it's held in-house, is good, validated company data and clean data. And we can also now cite the document that was used to answer any query. So distinct benefits that we get from this design. The design is essentially combining the two components on the left-hand side in a particular sequence, which I'll go through with you. Okay. Questions so far? Bob asks, I understand cost and energy consumption, but what are the risks incurred in training? The risks are that you come up with a model that you've spent a lot of money on that isn't answering the questions in the style that you want, Bob. And this is not uncommon. This is why the companies I've been mentioning that do foundation model training apply dozens, if not hundreds, of data scientists to the model training exercise. And let's say a machine in the middle of a 2-month-long training exercise fails, you might have to start again. You might have to restart the training. So there's lots of risk involved. So this technique I'm just going to show you sidesteps that whole risk and cost area by having a database into which your vector your private data goes. These are documents to do with GPUs, for example, inside VMware, or documents to do with the next release of VCF. That's private so far inside VMware, but a customer might ask us a question about it. It might be an investment report in a bank. It might be some guidance that an investor is giving to a customer, but it's private to the investment company, that sort of thing. And so there's a client application, which is typically a chatbot, and that client application allows Justin or somebody else to ask a question. That's called a prompt. And the question I'm asking here is, what is Llama Index? Llama Index was very new technology when I first built this slide. It's become well-known technology now. We'll talk about that later. So the first thing that happens to my question is it goes through something called an embedding model, which converts my question into numeric form. And then that numeric form of my query is supplied to the vector database. And what's going on in the query is, tell me about any documents that you have that relate to GPUs on VMware, for example, just an example question. The vector database comes back and says, I have these 10 documents that would be relevant to that query, and it supplies them to the controlling client application. And the client application then takes those 10 documents or chunks of documents and sends them with the original prompt question into the large language model. What it's doing is it's instructing the large language model, here are the answers I got from the vector database that represent realistic data. Here's the original question. I want you to massage all of that into a respectable answer to give back to the client application. Now, I've simplified it here. It's there's a bit more detail to it than that. But one of those details, for example, is that query encoder after prompt one there. That's actually a separate large language model to the completion large language model on the right-hand side. The completion large language model on the right-hand side, its job is to complete the answer. That's why I've called it a completion model. But there's a separate model running underneath the query encoder. That's called an embedding model. And there are many others here, but this is the general pattern that makes up retrieval augmented generation. And the reason this is going to be impressive when you have conversations with your own data scientists back home is most of them have heard of this. They're probably already using it, and they may have deployed something already on bare metal that uses this technique. And now they can do that on VMware Cloud Foundation very simply. So what we're going to look at now is some of the components in the blue layer, the VMware Private AI Foundation with NVIDIA. And we'll start off with, we've already seen the deep learning VM component, which is fundamental to everything. But we'll start off with the vector database and service automation. We'll move on to GPU management. And later on, we'll talk about model governance, which is a big subject in itself. And I'll make occasional references to the NVIDIA NIM, inference microservice is what that stands for. And I'll make some references to the NeMo retriever. That's fetching data out of the vector database, but details on those come for another day. That's NVIDIA software. You can learn a lot more on NVIDIA AI Enterprise at their website. So why VCF, first of all, for private AI? Well, as you've seen by now, data scientists spend a lot of their time in selecting which model is going to apply to a particular application that they're building. Some models are very good at creativity. Other models are very good at science. Other models are very good at text generation. Model selection is a whole field in itself, and we can advise the customer on that, but usually your data scientist will be well acquainted with this area. Then data scientists spend an awful lot of their time cleaning up data and setting up the environment that they can work in. And then they build the RAG design that I've just explained to you based on a database and a model working together. This is an iterative process where you're supplying questions to test how useful is this model and how useful is this database in answering questions. How accurate is it and how speedily does it respond? If it's going to wait 10 minutes to give me an answer, that's not good enough. And finally, you need to build an application using containers to use this model. The model in itself is very, very nice, and the retrieval augmented generation application design is very nice, but until it's used in a business application, then it's not really doing my business any good. So there is an application development phase. Now, that's one data scientist, one day in their life, perhaps a week in their life. But there are multiple occurrences of this in every business that I know of. There's more than one data scientist, and any one data scientist is operating on 2 or 3 or 4 of these at any one time. And all of these experiments that are on the horizontal axis here need to be separated from each other and safe from each other, and they're possibly using different tooling, possibly different operating systems, possibly different Kubernetes flavors, possibly different data sets and different models. So this becomes bewildering very quickly if you do this on bare metal. And so the virtual machine on the horizontal layer is the ideal unit of separation between these. And any one horizontal line might be multiple VMs within a group that we call a namespace, a separator or a resource pool for virtual machines. So isolation of this developer's work from another developer's work, the ability to repeat an experiment over and over again with different data sets, with all the conditions being the same in the VM. All of these things have convinced me that VCF or VMware Cloud Foundation is the platform. That's one thing. The second thing is we want to take all of the infrastructure concerns that data scientists spend a lot of time on today on the left-hand side, process automation, monitoring, what's my server for my model, serving infrastructure, machine resource management. How busy are my GPUs? Do I have room for more applications to run against these GPUs? All of these concerns should really be managed by our IT department that has been managing VMware forever. The things on the right-hand side, choosing models, doing feature extraction, etc., data verification, that's the real data scientist. We want to put the highly paid data scientists on that work, not on the infrastructure work that we want to take back and give to corporate IT and have those folks manage this workload, just like they're managing every other workload. So now, a brief pause here. If you have questions, please feel free to put them into the Q&A. How do you set the parameters for ingest? Peter's asked. That's a great question, Peter. I think you mean ingestion into the vector database of private documents. And that whole thing is done using an embeddings model, as I mentioned. There's a model for that, a large language model for that. But you do have to set parameters, as you rightly ask, like how do I chunk up my documents? Is it by paragraph? Is it by page? Is it by sentence? All of these things are data science questions, really. They're not infrastructure questions where you and I belong. There's a heavy infrastructure theme in the talk that I'm giving here, but we have actually written some white papers to guide you on how you chunk up your data and set the various parameters on your ingestion, so that you have some guidance from us on that. Big topic. We'll come back to that a little bit later. So in VMware Cloud Foundation, as you already know, there is a management domain and a workload domain. We separate out management concerns for reasons of performance and stability. And inside the management domain, we have VCF automation, VCF operations, and data services manager that you see in the middle there. These are tools that we'll be using for private AI to provision and control the environments on the right-hand side. So we ask you to create a workload domain, firstly, for AI, in which in that workload domain, there is at least one server with a GPU that has a GPU in it. The types of GPUs that we support today and that NVIDIA supports are the H100, which is a very contemporary one, the A100, which is a very good GPU. I have it in my lab. It's getting a little older now. It's 3 years old. And the L40S, which is a dual-purpose GPU that does both graphics and heavy-duty compute like AI. And we deploy VMware Private AI Foundation into that workload domain. And given that we've deployed it along with the automation and operations tooling on the left-hand side, we can now construct data scientist clusters. Cluster one contains an AI workstation here. I've just done one, but it could be many, could be as many as you have resources to support it. It's just a VM, a deep learning VM that contains all the tooling that the data scientist needs. Having tested their model, and I'll go through what testing a model means, having tested their model for accuracy and lack of bias and lack of hallucination, they would promote that model into a more scalable environment based on Kubernetes. Something like 90 or higher percent of AI applications are deployed onto Kubernetes in production. So a Kubernetes cluster, of course, is very familiar to us on VMware Cloud Foundation. Kubernetes is built into Kubernetes into AI into VMware Cloud Foundation. The support of GPUs is built in. There are some drivers that you need for GPUs. Those are accessible over the NVIDIA AI Enterprise. And so we're going to see multiple clusters used for different purposes in our demos here in a second. And we're going to load up these clusters with the appropriate tooling such that the data scientist feels very comfortable. Typically, we ask you to have 4 servers for the management domain and 3 servers for a workload domain, but you can consolidate that down to a smaller number of servers, and we've seen customers do that successfully, the consolidated design. So that's the target here, is to be able to provision these AI workstations and Kubernetes clusters in very rapid order so that the data scientist is not held up dealing with infrastructure and that they go straight to their work in data science. And how do we do this? Well, on top of the VMware infrastructure that makes up VCF, VMware Cloud Foundation, we enable the supervisor. The supervisor is itself a Kubernetes cluster, as you possibly know, but it's a special Kubernetes cluster whose job is supervising other things, supervising AI workstations or supervising AI Kubernetes clusters, of which there will be many. There will be many of these because you're going to have a development cluster, a testing cluster, a staging cluster, and a production cluster at the very minimum. So this is what an AI Kubernetes cluster looks like. It's just a VKS cluster, VMware Kubernetes Service Cluster, formerly called TKG cluster, that has been provisioned as a result of asking the supervisor cluster to do it. So our provisioning engine, VCF automation, goes to the supervisor cluster and says, this data scientist wants an AI workstation, provision a VM for that. It goes through that provisioning automatically. This other data scientist is ready to put their model into scale testing or pre-production testing, provision a Kubernetes cluster with GPUs, provision 5 VMs, as you see here on the left-hand side, and on top of those, provision the appropriate pods with the containers from NVIDIA in it so that the data scientists can provision their model on top of that. So all of that is automated. It's not done by hand. And it's automated on top of the supervisor. Previous names for that were workload control plane, IaaS control plane. We now just call it the supervisor and be done with it in the next release of VMware Cloud Foundation. It's really controlling everything here. It's controlling the life cycle of the AI Kubernetes cluster and the life cycle of the AI workstation, even though the AI workstation is just a fairly straightforward VM. And by the way, deploying an AI workstation is day one with private AI. That's how you get started. We have other things also in the mix here, data services VMs, which are built using the integration between the supervisor and data services manager. Data services manager provisions the vector database that's going to be used by the left-hand clusters to do the work. And we'll see this in demo form in a second. And we also deploy Harbor. We deploy Harbor because this world of AI development and production is full of containers, and we want a private repository of containers. We use this Harbor private repository for containers. It shows pods here, but those are the implementation of Harbor itself. We use Harbor as a local repository so that we can do this in fully disconnected mode, in fully air-gapped mode. so that we don't have to be connected to the internet when we're deploying these clusters on the left-hand side here. And that's an important point because many of our customers are highly private, and they want to deploy this in their own environment, completely disconnected from the internet as far as this environment is concerned. Previously, they've taken a DMZ VM and downloaded the containers from NVIDIA and stored them into Harbor so that they can be deployed in an AI workstation or an AI Kubernetes cluster. Question here, how do we know which GPU needs to be selected for the type of container workloads, and how do we plan GPU capacity? That's a great question. Thank you, Raj. I'll talk a lot more about GPU infrastructure towards the back end of this talk, but we give you an option that you're going to see in a few minutes here to select what we call a VM class. And the VM class has been predefined by the infrastructure people to have a particular GPU profile. And that set of VM classes is set up in advance, and it's used when I'm provisioning an AI workstation or an AI Kubernetes cluster. So that's how the GPU gets attached to the appropriate VM, and we'll go through that. Later on, we'll see how do we monitor GPUs to make sure they're being used adequately. So I will answer your question over the course of the next set of slides. Hold that question for a minute. Okay. Teddy asked, the VI workload domain has its own NSX edges separate than the ones that are in the management domain. Yes, there are edge nodes in the workload domain that are separate. You're right. Yeah. Okay, let's get into it now. We're ready. We've got all our terminology. We understand we have an AI workstation or deep learning VM and a Kubernetes cluster if we want it, and we can have as many of those as we need. We're not confined, as you'll see, with other vendors to one gigantic Kubernetes cluster, which they charge you for, by the way. Here, Kubernetes comes for free with VCF, and we can have as many workload clusters as we want to. The very first experiment I did with this a couple of years ago was I created a manual deep learning VM from the image that I showed you, the deep learning VM image that NVIDIA, that VMware supplies you. You can do that by hand if you really want to, or you can apply your own automation technology to doing it as well. We provide you with lots of shell scripts to do this. But I personally prefer to provision an AI workstation, which is another name for a deep learning VM today, because the automation takes a lot of the hard work out of it. And I do that really at model development time when I'm testing a model to make sure it's a good model for my production. Once I've tested the model, I will then take it forward into an AI Kubernetes cluster so that it can be staged and performance tested at scale, many copies of that model running at once, like we would with a 3-tier application, for example, so that I can make sure that this model will behave when it's under pressure from thousands of users, if it is successful. So that whole process of creating AI workstations and AI Kubernetes clusters has up to 50 steps inside our automation technology. You're going to see those in a few seconds. And so a lot of the hard work is taken off the shoulders of the VI admin person or the data scientist that could be using the screens that I'm about to show you to do this. So in VCF, in the currently shipping version of VCF, which is 5.2.1, the VCF automation technology, formerly called ARI automation, as you've seen here, provided private AI is installed and set up, you have two tiles here, one that are catalog items, we call them, one that provisions a Kubernetes cluster, one that provisions an AI workstation, and we're going to request an AI workstation in the demo that I'm about to do here. We've rapidly expanded this collection of things. So in the more recent versions, you have all kinds of flavors of AI workstations, like an AI workstation that does RAG, second from the right at the top there, or a Kubernetes cluster that does RAG, that has both the large language model and the vector database that supports RAG in it, retrieval augmented generation. You can just use a bare AI workstation that just has Python and PyTorch in it. That's what we'll do next in the next few steps here. I'm going to skip over this now. This is the answer to Raj's question. When I'm constructing my deep learning VM that's underlying my AI workstation that I'm building here, you can see the very first entry is called VM class. That's a compulsory entry. And these VM classes, there will be a set of options for them. These VM classes have been set up in advance by an administrator to have, in this case, a virtual GPU composed of one A100 40C, 40 gigabytes of memory, that is presentable to the appropriate VM that's under the covers, the deep learning VM that's under the covers. So that's where the GPU gets assigned, Raj, by virtue of the user of this automation tool specifying it right here in the VM class entry. And they give a username and password. They might switch on some metrics. They might be using Jupyter Lab, which is very common. And we'll see this in action here in a few seconds. I'm going to skip over this. What I'm doing here is constructing an AI workstation from a deep learning VM image that has all of this tooling already set in it. And at first boot time, this deep learning VM is going to go out to the NVIDIA GPU Cloud NGC, install the NVIDIA GPU driver, given the right access keys to do so, and then install a software bundle, which is in this case is PyTorch, the development environment that developers love. And we're going to do that in the demo here. Okay, let's go to the demo. So we're looking at VCF automation here, and we're going to request an AI workstation, which is pre-configured with GPU capabilities, but is pretty simplistic. It just has PyTorch notebooks running in it, Jupyter Notebook. So we fill in some basics here at the beginning. What's the name? What's the reason for this? And here's the key choice. I'm making a choice to use two A100 GPUs. This has been pre-configured for me. This VM class has been pre-configured for me ahead of time. I can change the data size. I can change the password to log in. And here's the second major choice that I make, and this could be a data scientist making this, is which bundle of software, these are all containers from NVIDIA, which bundle of software would you like to use? I would like to use Generative AI here, and I supply my key. This is a key that I've got from NVIDIA that allows me access to the various software bundles at the top here. Now, in the case of a disconnected environment, we would not ask you for this. We would ask you for a different key. But this is everything that the data scientist needs to do all on one page. They hit submit, and they're not doing any more work. The automation is now doing the work for them of constructing a single VM, which will look like this. These are internal steps in the automation process. It's using an underlying technology called cloud consumption interface. If you're familiar with Kubernetes, this is the Kubernetes style of building a deep learning VM. And at the end of the process, here's what the data scientists see. They see a simple URL link that allows them to enter their application and start using the environment without further ado. That whole process is 5 minutes from the time the data scientists specified what they wanted to the end of the process here, the end of the automation. Creation was successful. And we'll take a look at what was done under the covers because we're infrastructure people. We're keen to know what happened here. Well, a deep learning VM was created within a Kubernetes namespace called RAG-1. That's the name that I gave it. This deep learning VM is just another deep learning VM, which happens to have two GPUs attached to it here because I specified that in the VM class. And inside that VM, if we want to edit it and look more deeply, we can see what parameters it has as far as memory, hard disk. But interestingly, it's using two virtual GPUs here. So this VM, if we wanted to evacuate the host on which it is running currently, and we had another host with two A100s, we could vMotion this VM to that new host if we wanted to. not something you can do with anything else. So now let's look inside the actual VM itself. Let's SSH into it, which is something a data scientist might want to do. And now we're actually logged into the deep learning VM here, and we're going to execute a few commands to see what's been happening here. So the very first thing that started up was the driver was installed, and all of the logging data is there for the driver installation, because this can be quite a tricky procedure, installing virtual GPU drivers. It means going out to NVIDIA, getting the driver, getting your license organized, and we've taken care of all of that. You can see the very last line on this screen here says, assign the license that this person has for their virtual GPU driver. A lot of detail here, I'm not going to go into it. I'm going to show you another script which sets up the environment for the data scientist. It's downloading a large language model here. It's setting up the appropriate directory for that large language model, and it's going to NVIDIA GPU Cloud to get this. You can see that at the top. NGC is NVIDIA GPU Cloud. But the last instruction in the script, which is executed automatically, is Docker compose RAG running in a Docker with a YAML file specifying what exactly is in there. And if we were to look at the containers that are executing inside that deep learning VM, here we see the NVIDIA Retriever, which is retrieving data from the vector database. That second line from the bottom. Here's the inference microservice, that is the NIM that is running my main model, my Llama model. And here is the actual applications or container applications that are supported by containers that give me a chatbot. We'll see that chatbot here in a few seconds. And here's PG Vector running in a container. So if I were to exec into that inference microservice, that's called a NIM, as we saw in the early, we would see that it's running a runtime for models called Triton. It can also run other models, but here it's running Llama 2 7 billion on the right-hand side. So we know what model. That's the default model that we deploy for you. You can, of course, change this in the automation if you wanted to. You can adjust everything that's going on here, looking at the code in the automation if you wanted to. And here's where the model is stored, and here are the parameters to the model. So this is part of the answer to Raj's question about how do I set my parameters. We set the parameters for you in this file, but of course you can change these parameters if you so choose to. Data scientists like to do this at the command line, so that's why I showed you what's going on in the deep learning VM from the command line here. Okay, now that we've got our model running in our deep learning VM and we've got a database, vector database running, how does this model actually behave itself when it's being used by an application? So now we're looking at an application. This is a chatbot application. It's running the Llama 2 model on the top right, left-hand side there, Llama 2 7 billion. That's the model that's being used. And we're going to ask this application a question. What is Llama index? And submit that question. Now, the question went straight to the large language model under the covers this time. And it says, I apologize, but I really can't answer your question. This is not good. This is what happens when you ask a model about a subject that it wasn't trained on. It doesn't know the answer. So we're going to fix that by adding a file into our vector database that contains data that is pertinent to that question. Now, this would have been done in advance in real life. We've just added a data set into the vector database that's underlying this application, and we're going to go back now and ask exactly the same question again. But this time we've switched on the vector database. The knowledge base here is the vector database. Exactly the same question. What is Llama index? And this time we get a sensible answer. We get an answer that tells us Llama Index is a tool or platform designed to help large language models work with data sets. It's a tool for building RAG applications. So that's our very first application that we would suggest you build something like this. There are dozens and dozens of these chatbot examples, some available from VMware, some available from NVIDIA, others available out there that you could use as a starting point to get into this AI work if you chose to. Now, under the covers, we can look at this using Swagger. We can actually see what model is running here if we want to, and we can send it questions if we wanted to. These are low-level techniques for seeing what are all the parameters to my model here. And we'll stop the demo there. Okay. That's the first of a series of demos. What we did there was we provisioned a deep learning VM, and we loaded a bunch of tools into it, including RAG tools that were downloaded from the NVIDIA GPU cloud. We could have downloaded them locally in advance and started there. Now, here's the automation script that lay behind all that. You can edit that so for example, you can change the model. You can change the GPU allocation. You can change any of the parameters here in the automation script if you wanted to. And here is the collection of models that NVIDIA has out there on their GPU cloud. So these are recommended models that NVIDIA has tested for performance and made sure that they work fine. And here's a set of recommendations from NVIDIA, partly an answer to the question that came up earlier, which is, what GPU do I need to support these models? Here's an example of an H100 GPU. You'll need 2 of them to support this model, according to this site from NVIDIA, to get the best performance out of it. Okay. There was a question from Teddy during my demo there. I guess that's the dynamic direct path I/O mode. It will allow you to allocate entire GPUs to a VM. Dynamic direct path I/O is indeed a style of using NVIDIA GPUs on VMware. But I've used a more advanced technique in my demo so far called virtual GPU. Now, under the covers, there is direct path I/O going on, but virtual GPU gives me the special feature of being able to vMotion my VMs around in the data center that dynamic direct path I/O does not give me. I'll show you a chart in a short while that explains the differences between those 2 techniques, Teddy and Anastasios. So virtual GPU profiles are an alternative way of using the GPU to pass through or dynamic direct path I/O. There are alternatives that you can choose. I'm using virtual GPU here to get that advantage. Okay. Okay, so now let's deploy a Kubernetes cluster. We've deployed a simple deep learning VM. Let's deploy a Kubernetes cluster. A Kubernetes cluster is really a place where pods run, and those pods contain the data science technology that NVIDIA supplies at the top. On the right-hand side there, the NIM, the NeMo retriever, the network operator, the NIM operator. Those are all deployed automatically during the process I'm going to show you, deployed into pods inside my own AI Kubernetes cluster. That AI Kubernetes cluster was created by the automation technology using the supervisor cluster as the means of creation. So I get a collection of VMs. Each VM is a node in a Kubernetes cluster, and 1 or 2 of those nodes may have GPUs attached to it. That's my choice when I'm constructing it. And those will get the right drivers. Those VMs will get the right drivers as a result of the automation that you just saw here. So we can provision also data services manager like that. We can provision it and have it construct the Postgres and the PG vector that we talked about earlier to complement the large language model or augmented, as we saw. So the benefit we get from having Postgres under this is all of the replication, availability, backup, and access control apply that are built into Postgres today. So let's do a second demo now that shows a simple AI Kubernetes cluster. And we'll start this demo with another example of a chatbot that we'll use. Okay, so let me just get to the appropriate place for this. And this time we'll go to this one. So this is another example of the chatbot. We're going to ask it a question here. What's the process for configuring custom authentication settings in the latest version of my company's proprietary software? So this is now a customer service representative asking questions like I was asked here how do I control the authentication settings? And I submit that. These things here are parameters of the model that determine the randomness of the answer. And this model has said, I can't answer your question. So we're going to do the same thing. We're going to switch on the vector database, which has data inside it about XYZ software documentation. We're going to switch that on and go back here and turn it on and ask the same question again with it on and say submit. And this time, according to the company's internal documentation, the process for configuring authentication are steps 1 to 7. Much, much better answer. That was a Kubernetes cluster using a RAG design to augment their answer with a vector database. So what we're going to do now is we're going to request an AI Kubernetes cluster or an AI RAG Kubernetes cluster that has a chatbot application built exactly like we've seen. So we give it a name, and here we're making decisions about two different types of VM. First of all, the control plane VM, which we'll choose a particular VM class for. You can see VM class is a very important concept in all of this. And we'll choose the simplest possible Kubernetes cluster that has just one VM in it. And we'll choose, as you can see here from the various VM classes that have been set up, some of them have only got 4 gigabytes in them or 5 gigabytes. These are sharing virtual GPU profiles. These are the ability to use just a part of a GPU, whereas A140C is using all of a GPU that I'm using here. I supply some keys here. These are customizations to have it to go out to Hugging Face to get the model. But in one page, I've specified what VM class I want and what kind of RAG application I want, and I say submit. Now, in the background, VCF automation is executing 45 different tasks, which you would have had to do by hand or in your own automated way, which will take quite a long time if you do it manually. This is the benefit of automation. So at the end of that process, we see that something like 45 tasks have been done here. A lot of work, setting up the operators, which are the Kubernetes things, setting up NVIDIA, setting up the RAG design, a lot of different work gone on here. So if we go forward, all of the automation in the background has produced this page. And this page allows me to click into the application, and I clicked into the application. This is the running application, and this is exactly the application that we started out with at the beginning. So very quickly, within 15 minutes, we can go from scratch, having nothing, to having a running Kubernetes cluster that's now supporting an application with a chatbot running inside of it. Okay, that was demo number 2, demo 3 coming up. Okay. So what we saw there had quite a lot of prerequisites to it. It had private AI deployed with a supervisor, a workload domain. We ran a quick start process inside the automation, which sets up all the right parameters that you were asking about. We need some configuration tokens and keys from NVIDIA to have this all work. All of those things are applied. You saw me applying the API license, but all of these things are applied as part of the preparation step that we call quick start. I didn't demo that to you, but there are slides in my deck that show you what the quick start does here. Those are the prerequisites to doing what I just did in automation, in provisioning the cluster. Now, there's a series of slides here on NVIDIA licensing, how to get the license from NVIDIA AI Enterprise, and this is the portal that you can run on premises to do all the NVIDIA licensing on premises in disconnected mode if you wanted to. This is called a delegated license server. It's just a virtual machine running on your premises to handle all the NVIDIA licensing. And there's a whole user guide for setting this up and getting it configured in the right way. If you're cloud connected, however, you can go to the NVIDIA licensing portal that's running on NVIDIA's site, and you can get your licensing from there. You can see that in the icon in the middle of the screen there called NVIDIA Licensing Portal. And this is what the licensing portal looks like. It has the ability to control license servers and users and entitlements. This is a process that you'll get used to as you get into NVIDIA AI Enterprise. And that's where I got my licensing API key that you see here on the left-hand side to supply to the software. I won't dwell on this subject, but there are user guides to guide you through this subject. Here's what licenses look like when they're being used. These licenses, I've blanked out some of the names here to protect the innocent engineers that are using these keys. But this is what the portal gives you for management of your licensing keys of NVIDIA software. So, okay, so far we've talked about provisioning the data scientist environments automatically. Now we're going to go deeper into the GPUs. So inside VCF operation, you have this beautiful set of dashboards here. There are actually two dashboards today. There will be more dashboards in the future. But this dashboard has a colored block on it for every GPU on every server in every cluster in my enterprise. The green means okay, the red means needs attention. We colored this red deliberately because we wanted to show how underutilized the GPUs are in some of these hosts. So red doesn't mean danger here, it means underutilized. And you can choose that, you can adjust these colors. Probably blue or gray is a better color for underutilized condition, meaning it's not fully occupied at the moment. Yellow is it's partially occupied, and green is it's well occupied. And the names above the green blocks are the names of the hosts, and above those are the names of the clusters. And I can drill down on any one GPU, as I'm doing here, to find what is the sequence of clusters, vCenters, and hosts that contains the virtual machine with that GPU on it that is the subject of my attention because it's red. And I can see on the right-hand side for each physical GPU, which kind of GPU is it and how utilized is it. And I can compare utilization against power consumption, for example, if I wanted to see how efficiently I'm running my AI workload from a power perspective. So that's the topology for any one GPU. I can also see all the GPU-equipped clusters in the middle here. There are the clusters and the hosts in those clusters. And this one host has its GPU at 98.7% memory usage. That's not necessarily a bad thing. Memory is a premium on GPUs. And so if I'm occupying the GPU fully, as far as its memory is concerned, I'm using the GPU in a good way. I don't want to be using it at 99% all the time, but at least part of the time, it's okay. And there is drill down into the temperature of the GPU, the power used, the memory used, the cores used, the total memory. And I can compare this with other metrics as I'm doing on the right-hand side here. I can compare two GPUs against each other to find out how they're behaving. So this is day 2 now. I've deployed my AI application, and I'm interested in how efficiently I'm using my GPUs. So is there one question here, is there a private AI foundation playbook with the steps that I've given here deployed? Indeed, there is. There is a full set of documentation, and there's also a private AI guide and many, many blogs on private AI that I'll give you pointers to at the end of the talk here for more information on this. If you look up Private AI Foundation on broadcom.com, you'll get a lot of those pointers to documentation. There are lots of playbooks here for how to get started. So now, straying away from GPUs for a second here, this is a relatively new feature. It's the beginning of a whole new set of services for model storage. And I want to tie everything together now, tie the deep learning VM on the left-hand side with the AI Kubernetes cluster on the right-hand side, and show how they operate together using the Harbor repository as the join point between the two. So this is, if you like, a kind of summary of everything that we've talked about so far. And it's put in the context of a new model that a data scientist is pulling down from the NVIDIA GPU cloud, NGC, or from Hugging Face. Hugging Face is the global repository containing thousands of models, some of which are interesting for you to use. And you might use NVIDIA GPU Cloud's CLI here to pull down a model that is of interest if you're a data scientist. And we suggest that you bring that down into a deep learning VM that's in a safe namespace, a DMZ namespace to begin with, so that if that model is harmful in any way, its behavior will be controlled. Now, inside that deep learning VM, we're going to run a sequence of tests, and I'm going to show you some of these, that establish whether this model is a good model or a bad model. And so we think this environment will be provisioned by a new type of persona inside your company. Maybe it's a system administrator, or maybe it's somebody with a job title of LLM operations or AI operations. And those folks set up this deep learning VM, and the data scientist pulls down the model into it, and they run a sequence of testing that we're going to show you. And then once the testing is completed and they've found that the model is valuable and safe and not doing bad things, they will use a private AI Foundation CLI, command line interface, to push that model up into the Harbor repository that is the recognized library of validated models. We have one of these for internal work here, by the way, and we have a portal that shows it. And these models have been tested by data science people, and now they're ready to be pulled into runtimes for application scaling or application use. And that application will be built by a new service called an agent builder that we'll be shipping out to you in the future. And they can run that on a model runtime like the NVIDIA NIM or another runtime that we will supply. And they can make data indexing and retrieval, which is the loading of data into the vector database, much easier by means of a new service. All of that is running on top of Kubernetes on the right-hand side. So deep learning VM on the left, Kubernetes cluster on the right-hand side, running all of these functions that we'll supply to you to run them. My slides are going backwards here. So inside Harbor, we can have different projects for different products, and we can, within those projects, we can have different repositories with different models in them. So we're not just using Harbor now to store containers, as we've done in the past. We're using Harbor to store models that we've tested as a model store. These models have been tested by somebody and proven to be acceptable in every sense to the company, and now they're ready for use by applications. So this is part of the model governance story that I showed you a very high-level summary of at the beginning. So here are a set of projects inside Harbor, and inside those projects, I can have individual repos or repositories. We're effectively leveraging the open container interface here in the middle, which was built for storing containers. We're wrapping our models with some metadata that VMware supplies and storing the models into Harbor as a safe place within my company in which models will be kept. Because pulling down models from outside sources could be a risky venture. We want to make sure that only models are being used in applications that are of very high quality. So let's see that in action now. And this is going to be a short 5-minute demo of model governance. Let me get hold of that for you. Okay. So here now, we're going to provision a deep learning VM first, an AI workstation, and we're going to download a model from Hugging Face, get that model running, and test it using a set of tools which come under the title of Giscard. Giscard is an open source tool that allows me to see how well a VM behaves. So here I'm creating a deep learning VM into which I'm going to use the Triton inference server from NVIDIA. And I'm going to do that in order to test out a model that I've downloaded from Hugging Face. Here's the automation. I've now SSH'd into my new deep learning VM, and I'm running Triton there so that I can run models. That's the NVIDIA component that was downloaded for me. When I exec into that NVIDIA Triton container with a shell script, I'm now going to go to Hugging Face with my user ID and download a model that is of interest to me as a data scientist. I'm really a data science testing person here. So I'm now logged into Hugging Face, and I'm going to get Triton to pull down a model for me. Llama 3 8 billion instruct is being now downloaded into the deep learning VM and is ready to go there. You can see the file structure of the model on the left-hand side there. So now we're going to start that model up inside Triton and watch it running. And we're going to execute a series of tests against it. So run the model now. I've asked Triton to do that. The model is running. There's a whole bunch of ways of getting access to the model. One way is just to send it a post, a URL, an HTTP post is being sent here, and we're asking the model to write a script to generate prime numbers, just to see that the model is running. You can see the output there at the bottom is a sequence of Python text to run numbers. Now, this piece of code, I'm not asking you to understand it, but the core of this is we're using a framework called Discard to fire 500 or more individual questions that we've preordained to the model, and we're going to judge how high quality its answers are. So we're scanning the model for its performance, for its security, and for its reliability of answers. That's what this code is doing. It's a one-page Python script written by a colleague in engineering here. And actually, it's using a separate model to test my new model here. So we're using open source technology here to test our model, to make sure it's correct and safe. And we're going to run that model prediction script against it. And the results will show up as an HTML table. We'll see those here in a second. So now we're going to run that sequence of 500 question testing, and we're going to fire lots of questions at our model and see how it responds. We're using OpenAI's models to do that actually here. We could be using any kind of model to do it. So you're using a test model against my main model that I'm interested in. And as I can see here, there are some problems with that model that I downloaded from Hugging Face. Like it doesn't respond to some questions in quite the way that I would like to. Now, this is a job for a data scientist. They can supply guardrails around that model to tell it, do not respond to questions like that. Once they've done that correction of the model, we're now pushing the model up into the Harbor repository because it's been fully tested, it's been adjusted to behave correctly by the data science community, and now it's available in the Harbor repository and ready to go. So we can now pull that model later using this command here. So somebody comes along in a separate deep learning VM now, and they want to use that model. So this might be inside a Kubernetes cluster that they use the model, or it might be just a separate deep learning VM. And here's the model seen in the model gallery or model store with different versions and different conditions for it to be used here. So that's what the engineer did here was built a separate deep learning VM that's running Docker and capable of running that model in it. So that was a custom script that they've done here. They're now deploying that. And it's going to deploy a deep learning VM to do it. Okay. And here's the VM class again that you see at the top there. And okay, we've done our deployment. We'll execute that model. We pull the model into the deep learning VM from Harbor. This is done automatically by some of our newest tooling. And we can execute that model and see it working. There's the model working. We could make that all part of a CI/CD pipeline if we wanted to. We can see that the model is running because we submit a query to it and we get a description back that completes our work here. Okay. That was demo number 3, the full sequence of things from model download all the way through to model production. Okay. Getting close to the end here now. I promised you some information on GPUs. There are multiple ways of using GPUs on VMware, but one of them is the full virtual GPU style that you've seen me use. And that involves two drivers. Here's the GPU hardware inside my server. The first driver goes into vSphere itself. That's called the host driver. That comes from NVIDIA. That's automatically done by IT operations using Lifecycle Manager, for example. There's a second driver that goes into my deep learning VM or into my Kubernetes VM, and that's installed automatically by NVIDIA's GPU operator. I don't need to worry about that. We install that driver for you through the automation. But those two together, they need to be combined, and those are combined as a result of the automation script that I showed you. But you could install those by hand if you wanted to. I've done that, and I prefer the automation style of doing it, to be honest. For as far as installing the host driver, you can do that through Lifecycle Manager. That's how we do collections of machines that have GPUs here at VMware. We use Lifecycle Manager. We set up Lifecycle Manager to remediate the cluster with an image that's got the host driver in it, and we remediate the cluster, meaning all the machines will be updated with the latest host driver. You can set this up on the right-hand side, and there are instructions on how to do this. So let me skip over this one in the interest of time. We can do this offline if you're interested in that vGPU driver. Let me give you a little more details that are pertinent to the questions that came up. There are two ways at least of using GPUs on VMware, on VCF. One, as indicated by Raj's question earlier, is dynamic direct path I/O. And what that means is the full GPU must be allocated to one VM. You cannot share the GPU across two VMs. You cannot vMotion if you're in dynamic direct path I/O. Now, it's perfectly feasible as a way of working with GPUs if you're prepared to dedicate any one physical GPU entirely to one VM. No sharing, no vMotion. You might do this in early testing mode. Really, though, you want the ability to vMotion your virtual machines that have GPUs assigned to them. And for certain smaller jobs or small inference jobs, you might split up your GPU such that many VMs are sharing one physical GPU. An H100 has got 80 gigabytes or more of memory on it now. So you could have two VMs or more sharing that H100 GPU by virtue of the fact that they're using virtual GPU profiles that you saw me using when I was using VM class. And when you go to virtual GPU, there are two ways of organizing your virtual GPU, either to do round-robin time slicing, where every VM gets a time slice in a round-robin fashion, or where you actually dedicate part of the physical GPU to your particular VM. That's called multi-instance GPU, and that does more strict separation of one VM from another when they're sharing the same physical GPU. That's called MIG. You can also do with virtual GPUs the allocation of 1 up to 16 devices to one virtual machine. And you'll see me do that at the end of the talk here, where we have 8 GPUs in a host. And because we have a very, very large job to execute, we're going to dedicate all 8 GPUs, a very large model. We're going to dedicate 4 or 8 GPUs to one VM. We can do that in dynamic direct path mode. One to many can be allocated to one VM, or we can do it with virtual GPU mode. One to many can be allocated to one VM, one to many GPUs. And the benefit we get from the virtual GPU, of course, is the flexibility. So what's the difference then between time slicing and MIG? Time slicing is the ability to really equally share the time on the GPU in series between all the VMs that are sharing it. So if I have 10 VMs sharing the same GPU, which is not impossible, then each of the 10 gets a slice in turn, a time slice in turn in a round-robin fashion. For the time that the VM is using that GPU, the cores on that GPU are all available to that VM. So it's using the entire GPU for its time slice, and then it's relinquishing the GPU completely when somebody else gets its time slice. In MIG mode, we have separated the VMs on the GPU so that VM A gets half of the GPU and VM B gets the other half, and they never ever interrupt each other or interoperate in any way. They are spatially separated on the GPU itself. And that is done with up to 7 slices, as you see on the bullet in the right-hand side there. These two are NVIDIA technologies that we expose to you using something called a virtual GPU profile. These are virtual GPU profiles that are seen in the vSphere client, and the virtual GPU profile identifies the type of GPU that's been found in the hardware. These are automatically discovered, and they're fixed, by the way. And this GPU profile says, take all of that 80 gigabyte GPU and dedicate it to the VM that I'm giving this vGPU profile to. So the entire GPU is allocated from that A100. I could choose to allocate just 4 gigabytes or 5 gigabytes or 8 gigabytes or 10 gigabytes. I could choose to share in a time slice fashion that GPU among many VMs by using these profiles on the right-hand side. That's my choice at VM setup time. These profiles have 3 components, the word grid, the type of GPU, and the 4C, 5C, 8C in them. The next vGPU profile will be MIG profiles. These have 4 components in it, the grid, the A100, the number of CPU slices or GPU slices. This is the number of cores that are going to be allocated. Actually, it's a collection of cores. The 3 indicates 3 streaming multiprocessors, a collection of cores on the GPU. And you can see these profiles look different because they specify not just the memory in the 5C, 10C, 20C, but also a number that indicates how big of a slice of the GPU's cores am I going to get. And this means then that I can have 2 VMs executing on the same A100 with this 320C profile, each of which has roughly half of the GPU to itself. Never the twain shall meet. They will not overlap. They are physically separated on the GPU itself. Those virtual GPU profiles, when we go to Kubernetes, are encapsulated in something called a VM class that you saw me executed. You saw me using earlier when I was choosing my deep learning VM or my Kubernetes cluster. So this is how we wrap the GPU profiles in a VM class in readiness for you to use them. Now, there is more advanced forms of GPU that have these small devices on top of them called NVLink bridges that allow 2 H100 GPUs to behave as one. This is called an NVLink bridge. Each of those H100s might have 80 gigabytes of memory. 80 gigabytes may not be enough for a larger model, like a 70 billion model or a 100 billion model. So we can discover this hardware automatically at VMware and assign both of those GPUs with the NVLink between them to one VM. We can go even further than that. We can take all 8 GPUs that are on an NV switch setup here. That's an internal switch on a board built by NVIDIA called the HGX board. And all 8 GPUs can talk to each other if we so choose. Or we can segment them up into groups of 2s or groups of 4s and allocate those groups, which we call device groups, to individual VMs. So we can allocate the entire board of 8 GPUs to one VM, or we can segment them up into subgroups and give those to a VM as well. So as you can see, we're quite sophisticated in allocating modern multi-GPU systems to VMs. And these are the servers that we recommend you use either an L40S, an H100, or an A100. And those are the maximum number of GPUs that you see on them there. Some of them have 4, but as you see at the bottom, some of them have 8 GPUs in SXM format. That's an NVIDIA format of GPU. That's at the high end of these servers. This is all contained in a server guidance guide and in the VMware compatibility guide from VMware. If you look for VM Direct Path IO for general GPU, you'll get all the models of GPU that are currently supported on the VMware compatibility guide. And my final point is VMware Cloud Foundation is the platform for private AI, for doing this efficiently, doing this at scale, treating this as another workload that people manage the way they've managed VMware for years in the data center. You can get more information from us on this. There is a workshop that you can do with us. If you contact me at justin.murray@broadcom.com, I can give you the leads for that workshop. And there's a lot more resources on broadcom.com. Server guidance, validated solution, private AI guide, and lots of blog articles to help you through that and get you started. And thank you very much for your time. I think we have a couple of minutes for questions here, Ami.
Yeah, go for it.
Philippe asks, we are having some spare hosts, VDI hosts, which are equipped with older NVIDIA Tesla P100 GPUs. Is it possible to use this hardware? Well, that Tesla P100 is a very, very old GPU, Philip. The key indicator on it is how much memory does it have. It needs at least 20 gigabytes to do even a 7 billion model on it. So I would tend to look for a more contemporary GPU, but there's no reason you couldn't do experiments of your own on there with VMs if you want to. The P100 is capable of doing virtual GPUs, but it's a smaller GPU. We prefer GPUs with 40 gigabytes and higher on them, A100, H100, L40S. Those are the ones that are supported. L40S is the most like the GPU you have currently. In pass-through mode, we can MIG a GPU card and allow to different VMs. Well, in pass-through mode, you could deploy MIG on top of it. It's quite a complicated setup. We would prefer you to use virtual GPU for the purpose you want, Anastasios. So the method you suggest, if I put my GPU into pass-through mode, could I deploy, if you like, bare metal MIG on that? You could. That's been done. I'm not sure that's entirely supported today. What is supported is the use of a virtual GPU driver from the NVIDIA AI Enterprise Suite, and you can place that into MIG mode by using the NVIDIA MIG profiles that I showed you, the Grid A100 320C as an example. That's a great question. Is there a scheduler that can track resources and spin up down GPU-enabled VMs based on user requests and time frames? That's a question from Kyle. There isn't such a scheduler that spins things up on user demand, Kyle, inside private AI, but we have an API gateway coming in a future release of private AI that will give you somewhat similar functionality to what you're asking for. It will control access to different services over time. So that idea of a scheduler, a bit like Slurm in the high-performance computing world, that's not there today in private AI. It's a very good idea, though, so we are giving close consideration to it. Send me an email at justin.murray@broadcom.com if you'd like to discuss this a little bit more or get into private AI in a little more depth than I've done today. Other questions? Is MIG or time slicing mostly used preferred by customers? From Anuradha. MIG and time slicing are both used by customers today. What I would recommend is that if you're going to allocate multiple full GPUs to one VM, put those GPUs into time slice mode. If you have smaller inference workloads that can fit into 20 gigabytes of GPU memory, then time slice is a good option because it completely separates your VMs in the hardware of the GPU itself. Sorry, MIG is a good option for that. If you have smaller jobs that fit into a portion of a GPU, and you want to isolate that workload from any other workload that might be sharing the GPU, then MIG is a good option for that. But if, many of our customers are allocating two A100s or two H100s to one VM, those full GPU allocations, put those into time slicing mode is the recommendation. That's where we've done a lot of benchmarking to test this. And we've proven actually that the performance is within a few % of native performance for that particular setup.
Brilliant. I think that's all the questions answered. So thank you so much for the detailed presentation, Justin. It's been really useful content today. And thank you everyone for joining us. So as we mentioned at the beginning, this presentation has been recorded and your TAM will be able to make that available to you. If you had any follow-up questions that you think of following the session, again, please follow up with your TAM so they can reach out to Justin. Please join us next month when we'll be looking at troubleshooting capabilities and ARIA operations for networks. And we look forward to seeing you for that on May 15th. Thanks, everyone.
Thank you very much.